Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is generator synchronization. Our objective is to examine how synchronous generators are brought onto the grid, a process known as synchronization. Additionally, we'll introduce tools like synchronization lamps and synchroscopes used to manage synchronization events. And finally, we'll learn how our generator, once synchronized, can meet the real and reactive power needs of grid-connected loads. This lecture operates under the presumption that viewers watch the unloaded and loaded electrically excited synchronous generators lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now and return when you're so qualified. Fair warning. Generator synchronization is a fire-breathing, bat-winged, many-tentacled monster of a topic, and we could spend many hours mathing away the mechanical and electrical transients observed at the moment of synchronization, and many more hours mathing away the real and reactive components of exported electrical power, but I don't have time for this, and neither do you. In the interest of forward progress during the course of this lecture, I'm going to make broad sweeping generalizations, wholly inaccurate simplifications, and rather than involve you in the lengthy hunting, butchering, and cooking process, toss the fully cooked heart of this formidable monster on your plate and tell you to dig in. Let us begin the feast. We start with a small appetizer by way of a relatable, non-technical analogy. Viewers are no doubt aware that every action movie ever made must by law contain the following events: parkour, a gunfight, hand-to-hand combat, a car chase, a sex scene, escape from an unnecessarily complicated trap, and explosions. Really, the only thing that separates one action movie from another is the order, quantity, and sheer ridiculousness of the above scenes. If we were to zoom in on the mandatory car chase, the most entertaining and memorable car chase scenes often feature a totally believable scenario in which one guy pulls his car up to the side of the other guy's at full speed, only to fling himself out of his car into the other to finish the gunfight, knife fight, or sex scene. Key to the success of the car-to-car leap are the following essential elements. Both cars, understandably, need to be going in the same direction. Both cars need to be going at the same speed, and the cars should ideally be separated by mere inches. Then and only then can the guy make the perfectly timed car-to-car leap. Lacking any one of these elements, he bounces down the road. One can imagine generator synchronization as the car-to-car leap. Any generator wishing to jump onto an already established grid should understandably match the grid's direction, speed, and be separated by mere inches before making connection. Any excessive mismatch between the grid and generator may result in the catastrophic and costly destruction of the prime mover, the generator, coupling, electrical protection and distribution equipment, and/or your career and reputation. This is to be avoided at all costs. Moving away from the car-to-car leap analogy and into the technical content of this lecture, think of the properties that define three-phase AC, notably phase shift, phase sequence, frequency, and voltage magnitude. Only when the phase shift, phase sequence, frequency, and voltage magnitude of an isolated generator matches that of the grid is it safe for the generator to jump on board. A simplification of the generator synchronization uses a contactor separating the generator from the grid. When the contactor is in the deactivated open state, the generator works in isolation and is unsynchronized with the grid. When electrical power demand on the grid exceeds the present capacity of those generators already connected to the grid, additional generators need to be brought on board by synchronizing them to the grid. An operator wishing to synchronize a generator with the grid must use a stator exhibiting the same phase shift as the grid, rotate the prime mover in a direction such that the generator phase sequence matches that of the grid, adjust prime mover speed such that the generator output matches the frequency of the grid, and finally, adjust field current such that the generator voltage magnitude matches that of the grid. Only when the generator perfectly matches the grid, then and only then can the contactor separating the generator from the grid be closed. Doing so essentially places the generator in parallel with the grid, and the generator is said to be floating. Two important observations can be made about this lead up to a perfectly managed synchronization event. 1. For reasons we explained in the Unloaded Synchronous Generators lecture, the sequence of establishing the desired electrical properties matters. First stator, then direction, then speed, and finally field current, and finally timing. Any other order of events or attempts to shortcut or skip a step won't work efficiently, if at all. 2. The generator must match the grid and not the other way around. The grid has an ocean's worth of electrical inertia, and to think your tiny little squirt gun is going to change the tide is straight up wrong. Consider an occasion where the prime mover is rolling in the correct direction, at the correct speed, and field current has been properly adjusted to match the voltage magnitude of the grid. However, the rotor of the generator slightly lags that of the grid at the moment of synchronization, i.e. phase shift is off. Let's say we're rolling clockwise. Here's where the rotor is. Here's where it should be. Upon closure of the contactor, the overwhelming power of the grid will aggressively yank the rotor clockwise, as in motor mode, with a surge of electrical power into the machine and an equal and opposite surge of mechanical power out. Consider the exact opposite scenario, an occasion where again the prime mover is rolling in the correct direction at the correct speed, and field current has been properly adjusted to match the voltage magnitude of the grid. However, the rotor of the generator this time slightly leads that of the grid at the moment of synchronization, i.e. phase shift is off again, only this time in a leading fashion. Let's say we're again rolling clockwise. Here's where the rotor is. Here's where it should be. Upon closure of the contactor, the overwhelming power of the grid will aggressively brake the motor counterclockwise, as in generator mode, with a surge of mechanical power into the machine and an equal and opposite surge of electrical power out. As you might expect, these sudden surges of incoming and outgoing mechanical and electrical power aren't good, and if excessive can damage the prime mover and generator, not to mention the shaft, gearbox, coupling, fasteners, as well as electrical protection and distribution systems. In summary, not only is there a lot that can go wrong in generator synchronization, there's a lot of consequences if you do get it wrong, and only one way to get it right. One way of ensuring all goes well during synchronization is to continuously monitor and compare grid and generator output on either side of the open contactor. In the interest of expediency, we'll just check phase 1. However, keep in mind for a 3-phase AC system, you're going to have to do this check for all 3 phases. In a perfect world, the grid and generator voltage output traces would be essentially identical with the same frequency and magnitude at the same time. If you overlaid these traces on top of each other, at no time would there be an instantaneous voltage differential. This is what you are looking for, but it does not happen that way all the time. Here the prime mover is running a little fast, thus the generator's output has higher frequency than the grid. Do not close the contactor. Conversely, here the prime mover is running a little slow, thus the generator's output has lower frequency than the grid. Do not close the contactor. Here the field current is a little too high, thus the generator's output has higher voltage than the grid. Do not close the contactor. Conversely, here the field current is a little too low, thus the generator's output has lower voltage than the grid. Do not close the contactor. Damn, this is frustrating. As I mentioned previously, even if you got the speed and field current right, you still might mess up phase shift. Now keep in mind, phase shift really has 2 definitions for the purpose of synchronization. Not only does it mean the generator must have the same number of phases as the grid, it also means voltage for a generator's particular phase needs to match the grid's phase at the moment of synchronization. Here the generator's output matches the grid's frequency and voltage, however appears to be lagging behind the grid. Do not close the contactor. Conversely, here the generator's output matches the grid's frequency and voltage, however appears to be leading ahead of the grid. Do not close the contactor. To make matters worse, what if you screwed up the connections to the contactor linking the generator and grid? For example, if you went 1, 2, 3 for the grid and 2, 1, 3 for the generator, even if you had voltage, frequency, and phase shift correct, you'd still have sequence messed up. Believe me, you do not want to close the contactor with an incorrect phase sequence. As hopeless and as numerous as these do not close the contactor scenarios seem, they all involve one fatal flaw. That flaw being, different is bad. The overload traces show the obvious undesirable differences. Sure, there are brief moments when the generator and grid do happen to match each other, but quite like one of those songs from the hippie jam band Fish, most of the time they're offbeat and out of tune, and any fleeting moment of coherence is strictly temporary in nature. Anytime the contactor, essentially a low resistance switch, closes with a voltage differential across it, a massive surge of current can occur. Depending upon the instantaneous voltage values of the generator and grid at the time of closure, sometimes this current surges into the generator and sometimes out of it. All of these scenarios involve potentially high voltage across a low resistance switch at the moment of closure, a sure recipe for a massive surge of current. In summary, different is bad. Alternatively, one might phrase this as Same is good. Managed and timed properly, either side of the contactor at the moment of synchronization should have the same voltage, thus when it closes, no current surge occurs. Same is good. One way of ensuring proper synchronization is through the use of tools like synchronization lamps, synchroscopes, good old-fashioned voltmeters, and synchro-check relays to ensure the contactor separating the generator from the grid is closed only at the right time. Let's first examine how synchronization lamps are used to manage the synchronization process. Synchronization lamps are probably the simplest electrical instrument ever invented, consisting of a collection of 3 lamps placed in parallel to the contactor bridging the generator and grid divide. The principle of operation should be pretty self-explanatory. If you've reached this point in this lecture series, you are no doubt intimately familiar with Ohm's law, which states that current is equal to voltage over resistance. Given the lamps represent constant resistance, the current drawn through the filament, and thus the intensity of the light produced by the bulb, will be proportional to the voltage differential between the generator and the grid. When there is no differential between the generator and grid, no current will flow through the bulbs and they will be totally dark. When there's a small differential between the generator and grid, only a little current will flow through the bulbs and they will be super dim. Finally, when there's a massive differential between the generator and grid, lots of current will flow through the bulbs and they'll be super bright. Ideally, the contactor will only be closed when the synchronization lamps are totally dark, representing a moment in time when the generator and grid voltage perfectly match. Besides signifying moments of zero differential appropriate for synchronization, the lamps additionally perform other diagnostic functions to those accustomed to their use. Anytime there are infrequent matches in voltage, frequency, or phase, an operator will witness all 3 lamps slowly throb on and off. Whereas more numerous degrees of mismatch, an operator will witness all 3 lamps rapidly blink on and off. The more frequent the mismatches, the faster the blinking. Additionally, consider the worst case scenario, a phase sequence mismatch. This is immediately identifiable because all 3 lights would no longer illuminate simultaneously, but rather flash independently like the strobe lights at a Kiss concert. Synchronization lamps are clear, easy-to-use indicators of when it is and when it isn't appropriate to synchronize. However, because of their simplicity, they don't really give operators any clue as to which direction to go when a mismatch occurs. Is it too fast or too slow? Is voltage too high or too low? All you know is that there's a difference. For this reason, operators employ another synchronization tool known as a synchroscope. A synchroscope compares the frequency and phase of the generator and grid and makes use of an analog needle on a circular dial and indicates several properties simultaneously via direction, speed, and position of the needle. The direction of needle rotation indicates whether the generator or grid frequency is faster or slower. If the needle spins clockwise, the generator is faster than the grid and the prime mover needs to slow down. Conversely, if the needle spins counterclockwise, the generator is slower than the grid and the prime mover needs to speed up. The speed of the rotating needle indicates the degree of frequency mismatch. Consider a generator at 40 Hz and the grid at 60. This is a pretty heinous mismatch on the slow side, and the needle would spin rapidly counterclockwise. In response, an operator would increase the speed of the prime mover to meet the grid. As the frequency of the generator gets closer and closer to the grid, the needle would continue to spin in the counterclockwise direction, however it would spin slower and slower and slower. Ideally, when the frequency of the generator matches that of the grid, the needle won't spin at all. Conversely, consider a generator at 100 Hz and the grid at 60. This is again a substantial mismatch, this time on the too fast side, and the needle would spin rapidly clockwise. In response, an operator would decrease the speed of the prime mover to meet the grid. As the frequency of the generator gets closer and closer to the grid, the needle would continue to spin in the clockwise direction, however it would spin slower and slower and slower. Ideally, when the frequency of the generator matches that of the grid, the needle won't spin at all. Lastly, the instantaneous position of the needle indicates instantaneous phase mismatch. Consider a scenario in which the frequency of the generator perfectly matches that of the grid, however the rotor is leading 90 degrees in advance of the grid. In this case, the needle won't spin at all, but rather remains fixed at 90 degrees. Similarly, consider a scenario in which the frequency of the generator perfectly matches that of the grid, however the rotor is perpetually lagging 60 degrees behind the grid. In this case, the needle wouldn't spin at all, but rather remain fixed at negative 60 degrees. In summary, only when the needle of a synchroscope isn't moving and pointed straight up and down at 0 degrees, does the generator frequency and phase shift match the grid. Now this isn't as easy as it sounds, because you get sometimes dragged into this frustrating game of whack-a-mole where you're matching frequency but out of phase, or matching phase and out of frequency. However, you might find the natural fluctuations of a prime mover will eventually drift the generator into a match. When the needle stops moving, or at least is moving very, very slowly, at 0 degrees, it's time to close the contactor. Lastly, don't underestimate the importance of good old-fashioned voltmeter. While the synchroscope concerns itself with frequency and phase, a voltmeter can be used to compare generator and grid voltage magnitude. By adjusting field current, the voltmeter measuring generator voltage magnitude should match the voltmeter measuring grid voltage magnitude. Taken all together, a generator is synchronized to the grid only when all 3 synchronization lamps are off. The synchroscope needle is not moving and pointed at 0 degrees, and the voltmeters measuring generator and grid voltage magnitude are equal to one another. Then, and only then, can the contactor be closed. If this all seems like too much to manage with too big of consequences if you get it wrong, you're not the only one. For this reason, automated synchronization methods exist that do not rely upon the subjective interpretations and shortcomings of dim-witted human operators. We'll examine closed-loop controls and protective relay schemes in much later lectures that make use of a synchro check relay, which, as the name implies, permits synchronization only when certain circumstances, i.e. matching voltage, frequency, phase, and sequence are met. Presuming these conditions are met, the moment has arrived. It is time to close the contactor. In a perfect world, nothing happens. But even the best managed synchronization events can induce temporary electrical and mechanical transients. It's perhaps best to illustrate these effects with a practical demonstration.